Tonight we're talking about something that exists at the edge of everything we think we understand about our solar system. Something small and cold and distant. For almost 80 years, it was a planet, counted among them, ninth in line, a full member of the planetary family. Then it wasn't. And that shift from planetary status to something else entirely tells us a story about how science works, about discovery, about how we name the world, and about how we handle it when the world doesn't fit the categories we've created for it. This is not a story about a mistake being corrected. It's a story about how our understanding evolves, about how we define things, about what happens when certainty meets complexity. Pluto sits out there in the cold darkness beyond Neptune, small and distant and stubbornly mysterious. It was found by accident through mathematical prediction and careful observation, named for a god of the underworld, and eventually demoted from a status it held for nearly a century, a status that had seemed permanent and unquestionable. But before we understand what Pluto is now, or what happened to its planetary status, we need to understand how it was found, why people thought it mattered so profoundly, and what happened when better instruments showed us the truth about what we were actually looking at. We need to understand the assumptions that were made along the way, so take a moment, subscribe if you genuinely find this stuff interesting, let me know where you're watching from and what time it is, and let's explore the journey of a world that taught us something profound about how little we sometimes know about the space we live in, and about how careful we need to be with our certainties. In the 19th century, something strange was happening at the edge of the solar system. Neptune, the farthest planet known at the time, was not moving through space the way it should. Mathematicians studying its orbit noticed irregularities. The planet drifted slightly from its predicted path. It would be a few seconds of arc here, a fraction there. Small, barely noticeable, but measurable, but real. Something was pulling at it. Something invisible and distant was exerting gravitational influence. This had to be true. The only way to explain the observations was through the presence of another body. This was not speculation. The math was reliable, tested, precise. Orbital mechanics had proven themselves over centuries. Newton's laws had explained the movements of planets perfectly. The calculations that predicted planetary positions were among humanity's most successful intellectual achievements. Precision engineering had been built on these calculations. Navigation relied on them. The entire modern world depended on orbital mechanics being correct. If Neptune wasn't where calculations said it should be, then the only logical explanation was that another body existed beyond it, pulling through gravity at the planet's trajectory. Pulling the planet slightly away from its predicted position, the perturbation was small but detectable. It was measurable. It was real. It was undeniable to anyone looking at the data carefully. Astronomers became obsessed with finding this hidden world. It became a puzzle, a mathematical ghost story, a mystery hidden in numbers. If the math predicted something, surely it existed somewhere out there. This was the logical conclusion. This was what people who believed in the power of mathematics had to believe. Believe it or doubt the entire foundation of science. The search was on, urgent and serious. But the search for an invisible object in the vastness of space is different from looking for something you can see. You need location, you need confidence, you need to know roughly where to point your telescope. You can't just look everywhere randomly. Space is too large. The sky is too vast. Even a powerful telescope can only see a small portion of the sky at any time. You need predictions narrow enough to actually guide observation. You need mathematics to tell you where to look before you can look. Throughout the late 1800s, multiple observatories attempted the hunt. Some claimed discoveries, some were wrong. Errors happened frequently. False positives occurred and then were debunked. The math said something was there, but the confirmation refused to arrive cleanly. It was maddening to people who trusted calculation above all else. If your math was right, where was the object? Why couldn't you find it? Why did the sky refuse to give up its secret? By the early 1900s, the search had become something of an obsession in certain circles. This was not casual curiosity or idle speculation. This was serious business. This was about validating the power of mathematical prediction, about proving that invisible things could be known through pure reason and calculation alone. Observatories competed fiercely. Nations took interest in who would make the discovery. Prestige was at stake. Scientific glory was on the line. The discovery of this invisible body would be a triumph of intellect, a proof that mathematics could reach beyond what the eye could see. It would be a victory for prediction itself. It would show that the mind could know what the eye could not see. Decades passed slowly. Telescopes improved in power and refinement. Optics advanced. Glass manufacturing improved. Mounting systems became more stable. Photographic plates replaced direct observation increasingly, allowing faint objects to be recorded and studied later in the comfort of observatories. Photography was revolutionary in every sense. You could now capture images of objects too faint for the eye to see, objects that would be invisible to a human observer no matter how powerful the telescope. You could examine these images carefully, measure them, compare them to other plates taken nights or weeks or months later. The technology was advancing, moving forward, improving constantly. Yet the invisible planet remained invisible. It became a symbol of human reach, exceeding human grasp, of wanting to know something so badly that the absence of evidence became evidence of absence of effort rather than evidence of the thing itself. The hunt became metaphorical. The search took on almost mythic proportions. By the 1920s, the hunt had continued for so long that it had become institutional. This was not one astronomer's pet project anymore. It was embedded in the work of observatories, in their budgets, in their professional identities. Lowell Observatory in Arizona had been established partially around this specific search. Its founder had dedicated significant resources to finding this mysterious planetary body. Finding the planet would validate the entire institution's reason for existence. It would prove that Percival Lowell's vision had been correct all along. It would show that his faith in mathematics and prediction had been justified completely. It would be vindication. The story of Pluto's actual discovery begins not with a grand search, but with a photograph. In 1930, at Lowell Observatory in Arizona, a young astronomer named Clyde Tombaugh was examining photographic plates taken through the observatory's telescope. He was systematic, methodical, patient in his approach. This was not dramatic work. It was careful, meticulous comparison. The kind of work that doesn't make headlines or capture the imagination. The kind of work that requires attention to detail and the willingness to look at thousands of images without finding what you're searching for. Hours of work with small results. Days of searching with little to show for effort. Tombaugh had come to Lowell Observatory as a young man with a passion for astronomy, but without formal training. He had learned on the job, taught himself, developed skills through practice and determination. He looked at plates taken of the same region of sky on different nights, often 6 days apart. If something moved between those nights, if something was orbiting the sun, it would show up as displaced between the two images. The shift would be small but detectable. The technique was simple in concept. The execution was tedious and required patience. It was the same method that had been used for decades in the search for the unknown planet, but something was different this time. Tombaugh was young. He had energy and enthusiasm. He had focus and determination. He was not yet tired from years of failed searches. He was not yet cynical about the possibility of success. He had not yet learned that many searches end in disappointment. He brought fresh perspective to the work. Something was about to be found. On February 18th, 1930, Tombaugh noticed something that made him pause. A faint point of light appeared on one photographic plate that had moved slightly on a second plate taken 6 days later. Movement. Not much, not dramatic or obvious, but unmistakable and consistent with the mathematical predictions, consistent with what the calculations had predicted decades earlier. The object was where it should be. The position matched the calculations. The motion matched the predicted motion. He had found something real. The invisible planet was becoming visible. The position matched exactly what mathematicians had calculated should be there. The correspondence was striking. Verification came quickly. Other observers examined the same region of sky. The object was confirmed as real. The discovery was confirmed independently. Multiple astronomers looked and saw the same thing. The invisible planet was now visible at least as a faint spot on a photograph, barely distinguishable from the countless stars surrounding it. But there, definitely there, it was there. It had been found after decades of searching. The news spread quickly and widely around the world. The New York Times reported it prominently on its front pages. Radio stations announced it to the world. Newspapers picked up the story. It was major news. Here was the invisible world, finally photographed, finally captured, finally pulled from the realm of mathematics into the realm of observation. A triumph of science and mathematics, a victory for prediction itself, a vindication of the power of human reasoning. Clyde Tombaugh became famous overnight. Lowell Observatory became even more famous. The observatory's prestige soared. The hunt that had lasted decades was over. Telescopes around the world turned toward the object. Observations poured in from around the world. Every observatory with equipment capable of detecting it began studying it. Data accumulated rapidly, but something became immediately apparent as observations accumulated. Something odd. This world was strange. It was much smaller than expected. Much, much smaller. Calculations had suggested something more massive, something with greater gravitational influence, something more obviously necessary to explain Neptune's peculiar orbit. The mathematics had predicted a certain minimum size for an object capable of causing the observed perturbations. Pluto didn't match those predictions, and yet, here it was, small, faint, real. Real enough to photograph, real enough to track across multiple plates, real enough to demand a name, real enough to change everything about how the solar system was understood. The process of naming a newly discovered planet was not chaotic or arbitrary. There were traditions, conventions, diplomatic considerations. The process had evolved over centuries of planetary astronomy. Careful thought went into it. Precedent mattered. Lowell Observatory, having made the discovery, had some say in the naming, though not absolute authority. The power to name was not concentrated in one institution. The international community of astronomers had weight in such decisions. Scientists from multiple nations had input. Proposals came from around the world. Ideas were debated. Suggestions were made and considered. Many suggested names related to the god of the underworld. The logic was classical and straightforward and compelling. After all, Neptune was the god of the sea. Jupiter was the king of gods. Saturn was the god of agriculture and wealth. The next world outward, in the deepest darkness, in the cold beyond what was known, should belong to a deity of the underworld, a god who ruled over darkness and distance and the realm of the dead. Who better than Pluto? Who better than the god of the dead, the god of the underworld, the god who controlled the hidden realms beneath the surface of existence? Who better to rule over a world in the deep darkness at the edge of the solar system? It fit perfectly. Pluto made sense. It was classical and elegant and appropriate. It fit the pattern of planetary naming that had been established over centuries. It suggested something distant, something dark, something appropriately foreboding. The name carried meaning beyond mere identification. It carried metaphor and symbolism. It carried history and classical allusion. The name was not universally the first choice everywhere. Some proposed alternative names. Some suggested keeping the mathematical designations that had been assigned before the physical discovery, designations like Planet X. Some proposed names from other mythological traditions, but Pluto gained support as the discussions continued. Arguments were made for it. People advocated for it. It was lyrical and poetic. It was easy to pronounce in multiple languages: English, French, German, Spanish, Italian, and others could all say it without difficulty. It had that appropriate sense of gravity and distance. It connected the New World to ancient tradition and classical learning. In March of 1930, roughly 2 weeks after the photographic discovery, Pluto was officially named. The astronomical community accepted it. The discussion ended. The decision was made. The word went out to the world. The world had a new planet, the 9th planet, the outermost world in the solar system. It seemed settled. It seemed final, complete and definitive. A mystery solved through mathematics and photography. An invisible thing made visible and real. A mathematical prediction confirmed by observation. A name assigned and accepted. Order restored to the solar system. Cosmic order and structure restored. Pluto had joined the family of planets, the 8 others that had been known for centuries or millennia. It took its place among them. It would remain the 9th planet for nearly 80 years, for 8 decades, for multiple generations of astronomers, for a lifetime of study and observation by individual scientists. No one at that moment imagined it would be stripped of that status. No one at the ceremonies and celebrations anticipated that the confident assertion of planetary status would be so thoroughly questioned by future generations. No one realized that this naming was not the conclusion of a story, but the beginning of one, the beginning of a transformation. The excitement of discovery is often based on assumptions that look obvious until they don't. This would be the first of Pluto's major transformations. It was found, it was named, it was celebrated. But the question of what it actually was, that question was just beginning to form. Once Pluto was photographed and named, astronomers rushed to learn more about it. The discovery had opened a door that everyone wanted to walk through. Telescopes were trained on the distant point of light. Photographs accumulated rapidly from observatories all over the world. Measurements were attempted with the best instruments available. Spectroscopy was applied to determine what the object was made of, to understand its composition, to learn whether it was more like rock or ice or something else entirely. Every technique that astronomy had developed was aimed at extracting information from that faint object at the edge of the known solar system. What emerged was puzzling, deeply, fundamentally puzzling in ways that no one fully articulated at the time. Pluto was very small, much smaller than any other planet, even smaller than the Moon. It was tiny, a distant point of reflected sunlight, barely bright enough to be photographed at all. It was a challenge to observe. You could almost mistake it for a star if you weren't looking carefully, if you didn't know what you were looking for. The brightness of an object in the sky depends on 2 things, fundamentally and obviously. How much light it actually produces or reflects, and how far away it is. Simple in theory on paper. The calculation is simple in concept, but complicated in application when you're dealing with an unknown object, an object you're trying to understand. The inverse square law applies. But if you don't know all the variables, if information is missing, your answer will be uncertain. For a distant object, calculating size becomes a guessing game with limited information. You're trying to work backwards from incomplete data. If Pluto appeared so faint to observers, astronomers had to make assumptions about what that faintness meant. Was it small and moderately reflective? Was it larger, but made of dark material that absorbed most light? Was it something else entirely? Was it made of material with unexpected reflective properties? The math could work multiple ways. Many different combinations of size and composition could explain the observed brightness. Early estimates were crude because the information available was limited. Parallax measurements were difficult because Pluto was so far away. Direct size measurements were impossible. Astronomers had to infer size from brightness, and those inferences carried large uncertainties. The error bars on size estimates were substantial. Its surface was impossibly cold. Temperatures in that region of space, so far from the sun's warmth, would be extreme beyond anything on Earth, beyond anything humans had experienced. The sun appears tiny from Pluto's distance, roughly 39 times farther from the sun than Earth is. From Pluto's perspective, it's just another bright point in the sky, prominent but distant, unable to warm the surface of the world. The heat that reaches that far outer region is minimal, a whisper compared to the radiation that bathes the inner solar system. Whatever Pluto was made of, it was locked in a deep freeze. Ice would be solid as rock, harder than rock in some ways. Gases would condense into liquids or solids. Methane would be ice. Nitrogen would be ice. Ammonia would be ice. The entire world would be locked in frigid stasis. Its atmosphere, if it had one, was strange, exotic, unlike anything in the inner solar system. Most planets have atmospheres that are mostly nitrogen and oxygen, or hydrogen and helium. Pluto was different. Early spectroscopy suggested something unusual about it. Something involving methane, perhaps. Something involving frozen volatiles that would be gases elsewhere, but solids in that deep cold. The composition was uncertain, but clearly exotic compared to familiar worlds. Its orbit was weird. It didn't follow the nice plane that all the other planets occupied. It tilted at an angle, inclined relative to the standard orbital plane. It wandered in its path. It crossed the orbit of Neptune sometimes, creating situations that should have been impossible if standard planetary rules applied. Though the two bodies never came dangerously close, the possibility existed mathematically that at some point in the distant future, an interaction could occur. For a mathematical body designed to explain Neptune's orbit, Pluto was strangely unlike the other planets. It shouldn't exist where it was. It shouldn't orbit the way it did. The orbital peculiarities should not have been possible according to how we understood planetary formation. Everything about Pluto seemed to violate the conventions of planetary existence. Everything about it broke the rules. It was an exception, an outlier, and yet it was still called a planet. It had been named officially. It had been discovered and celebrated by the world. Questioning its planetary status meant questioning the discovery process itself, meant questioning whether the finding was real or somehow mistaken. That was not something the astronomical community was eager to do in 1930. The discovery was too recent, too celebrated, too important to the reputation of Lowell Observatory and to the legacy of Percival Lowell, who had predicted the existence of such a body decades earlier. So Pluto remained a planet, despite its strangeness, despite its small size, despite its odd orbit, despite everything that made it different from the 8 planets that had been known since ancient times or early telescope history. Scientists studied it methodically and carefully with their available instruments. New measurements came in gradually over time. Photographs accumulated from around the world. Spectroscopy revealed composition hints and clues, though never with complete certainty or confidence. Dimness made observations difficult. The object was so far away from Earth, so poorly lit by the distant sun, so small that basic facts were hard to pin down with any confidence. What was its exact size? How massive was it really? What was its density? What did its surface look like? Were there moons orbiting it? The questions multiplied much faster than the answers arrived. Each new technique applied to Pluto revealed new complexity. But there was no rush, no urgency. Pluto was classified. Pluto was named. Pluto was a planet. The mystery was solved. Or so everyone believed. The catalogue was complete. The solar system understood. The 9th planet had been found, and everything fit neatly into place. The picture was complete. Future observations would reveal that the mystery was not solved at all. It was only beginning to be recognized as something far deeper and more complex than anyone had anticipated. From 1930 through the 1950s and beyond, the entire astronomical community held a set of assumptions about what Pluto was. It was the 9th planet, the smallest, the coldest, the most distant and most difficult to study. It was a failure of initial prediction in terms of size, but it was there in reality. It was real. It had been photographed. It had a name. The planetary status seemed settled, complete, final. But underneath this comfortable certainty, assumptions were quietly building that would later crumble under scrutiny. One fundamental assumption was about size and composition. Because Pluto was so faint, early estimates of its mass were crude at best. Astronomers knew it was small, but how small? That was the question. They made assumptions based on how bright it appeared and how far away it was. Those calculations are based on a formula that depends on multiple variables. If you know distance and brightness, you can infer size. But if you don't know distance precisely, or if the object is made of unusual material, or if there are unknown factors, your calculations could be completely wrong. Those early calculations suggested Pluto had a mass roughly equivalent to Earth, perhaps a bit less. A significant world. If Pluto was that massive but appeared so small, it would have to be made of unusual material, perhaps stone and ice compressed into extreme density. Or perhaps their brightness calculations were wrong or incomplete. Perhaps Pluto was a bit larger than initial estimates suggested. Perhaps it was darker than they thought it was. Perhaps the composition was something unexpected and unusual. These questions remained open. They hung there. They created uncertainty that no one wanted to fully acknowledge. Observations improved slowly, incrementally. Each new measurement refined the picture slightly, but Pluto remained a mysterious object at the edge of understanding. The problem was fundamental. Pluto was so far away, and telescopes of the era, while improving continuously, still had clear limitations. Photography helped tremendously. It was revolutionary. But even with photography, Pluto was a barely detectable speck. Radio astronomy wasn't yet available. Spectroscopy gave hints about composition, but not definitive answers. You could detect certain elements, but the information was limited. You could infer, but inference is not proof. Observers had to work with what they had. They gathered data carefully. They published papers. They argued about interpretations. The scientific process was slow, methodical, and dependent on equipment catching up to curiosity. Pluto became the 9th planet, the distant oddity, the exception that proved the rule, the object that didn't quite fit the pattern but existed anyway. Everyone accepted that. Everyone moved forward with that assumption. Another assumption was that it was unique. The solar system had 9 planets now. The hunt for the 10th was not particularly active. Why would it be? Pluto was strange, but it was the 9th. The search had succeeded. Why look further? The region beyond Neptune was assumed to be empty, just Pluto floating alone in darkness and distance. This assumption went largely unquestioned because it seemed reasonable, it seemed complete. The solar system had been known for centuries. The major bodies had been identified. Every major gravitational body in the region should have been noticed by now. Pluto was the last piece of a puzzle thought complete, finished, done. No one seriously considered that Pluto might be one of many, that entire populations of objects might exist in the deep cold regions beyond Neptune. That idea had not yet crystallized in mainstream astronomy. The concept of Kuiper belt or Oort cloud existed in theoretical discussions among a few scientists. Gerard Kuiper had proposed ideas about distant populations of icy objects. But these were hypotheses, speculations about where comets might originate, how material might be distributed at the edge of the solar system. Interesting ideas, worth thinking about, but unproven. No one had observed these populations directly. No one had proven they existed in any concrete way. So they remained theoretical, interesting to consider in academic discussions, but not changing how Pluto was understood or studied in practical terms. Pluto was treated as singular, as unique, as the final answer to the question of what lay beyond Neptune, the singular object, the only thing. A third assumption was about what defined a planet. For centuries, maybe millennia, planetary status had meant essentially being a major body orbiting the Sun. The 8 known planets before Pluto were all large, all in relatively circular orbits in the same plane, all apparently unique in their regions. They had characteristics in common: size, orbital behavior, isolation from others of their kind. Pluto fit almost none of these criteria, yet it had been promoted to planetary status anyway. The definition was vague. Intentionally so, perhaps. There was no official list of requirements. There was no formal criteria written down. There was no rule book. Pluto was a planet because it had been discovered and named and seemed important enough to matter. It was a planet because it had been found through mathematical prediction, which gave it prestige. It was a planet because the discovery was celebrated globally. It was a planet because taking away that status would require admitting that the definition was flexible or incomplete, or had never been properly established. The question of what actually made something a planet was not rigorously addressed. Astronomers assumed they knew intuitively what a planet was. They could point to the 8 classical planets and say, "These are planets. See?" But when asked to define the criteria explicitly, the definition became fuzzy. Astronomers assumed they knew, but the assumption was never tested because it had never been seriously challenged. How do you define a planet? Is it size? Is it orbital characteristics? Is it composition? Is it simply being round and orbiting the Sun? Is it gravitational dominance in its orbital neighborhood? Is it something else? No one had to answer these questions as long as the 8 classical planets remained obviously planetary, and Pluto remained a strange anomaly, accepted anyway through inertia and tradition. These 3 fundamental assumptions shaped how Pluto was studied, discussed, and understood throughout the second half of the 20th century. It was the 9th planet. It was strange and distant, but it was definitely a planet. It was unusual but not challenged. It was small but still counted. It was alone but assumed to remain so. No serious challenge to that status would emerge for decades. Decades would pass. The acceptance was broad. The status was stable. everyone agreed. The scientific community moved forward with these assumptions embedded in their thinking, in their textbooks, in their teaching of the next generation. These three assumptions created a particular way of thinking about the solar system that persisted for decades. The assumptions reinforced each other. They formed a stable framework. Textbooks were written based on them. Students were taught using them. A generation of astronomers grew up with the idea of a 9-planet solar system, with Pluto as the unique solitary ninth. The idea became conventional wisdom. It became truth through repetition and institutional reinforcement. It became what everyone knew. No one questioned it because the questioning had already been answered. Pluto was a planet. End of story. The door was closed. The question was settled. The answer was known. There was no need to revisit it. But closed doors, once settled questions, and comfortable certainties have a way of being reopened by new evidence and new technology. The cosmos was patient. The universe had time. What seemed settled in 1930 would seem entirely different by the late 20th century. New tools would be invented. Technology would improve dramatically. New observations would be made. The Kuiper Belt would transform from theoretical speculation to observational reality. Discoveries would mount. Objects would be found. Pluto would be seen not as the end of the planetary system, but as the beginning of a new one. The object that seemed unique would turn out to be one of thousands, maybe tens of thousands. But that transformation was decades away. For now, in the middle of the 20th century, Pluto remained secure in its status. It remained the 9th planet. It remained mysterious and distant. It remained alone, or so everyone believed. The assumptions held. The framework was stable. The certainty was strong. Meanwhile, the cosmos kept its secrets about what Pluto really was and what else might exist in those dark regions beyond the sun's warmth and light. Secrets that would not be revealed until technology advanced far enough to see what had been hidden in plain sight all along, until instruments could detect the faint objects orbiting beyond Neptune in the cold and darkness, until the universe could reveal what it had been keeping hidden, what it had been concealing in the outer reaches of the solar system. Until astronomers were ready to question the comfortable assumptions they had accepted so readily, assumptions that had hardened into fact through decades of repetition. The cosmos waited patiently for that moment. The cosmos waited patiently for that moment. But moments, in science, often take decades to arrive. Sometimes longer. Sometimes entire generations pass before what seems certain becomes uncertain. It wasn't until the late 1970s that something unexpected happened, something that would begin to crack the comfortable certainty surrounding Pluto. The crack was small at first, barely noticeable, but it would eventually widen into a chasm that couldn't be ignored. New instruments came into being throughout the 60s and 70s. Better telescopes, more sensitive detectors, technology that could reveal things the older equipment had simply missed or misunderstood. Photography was being supplemented by electronic detection. Charge-coupled devices, CCDs, were invented. These were revolutionary in their way. They were more sensitive than photographic plates, far more sensitive. They could detect fainter light. They could measure brightness with greater precision. They could record information that had been invisible to the photographic process. And as these instruments turned toward Pluto, as astronomers began using this new technology to study the distant world, something became immediately apparent to anyone willing to look carefully. The data didn't match the old estimates. Pluto was brighter than the calculations suggested it should be. If Pluto was really as small as everyone thought it was, If the size estimates from the original discovery were correct, if the mass was what had been calculated, then the brightness readings didn't make sense. They contradicted each other. The math wasn't working. Either the object was larger than was believed, or it was made of material that reflected light differently than expected, or something else was fundamentally wrong with the assumptions that had been made decades earlier when the planet was first discovered and named. Scientists began to reconsider their understanding. What if Pluto wasn't as massive as the size estimates suggested? What if the earlier calculations had been fundamentally wrong? What if the object was even smaller than anyone had thought, not larger? The possibility was disturbing in its implications. If Pluto was actually smaller than calculated, then the gravitational influence it exerted on Neptune would have been negligibly small, almost nothing at all. That meant the theory that had justified its discovery, the entire foundation that Pluto was placed there to explain Neptune's orbital irregularities, that theory would be fundamentally undermined. It would collapse. The perturbations that had been attributed to Pluto might have been caused by something else entirely. They might have been observational errors made by early astronomers. They might have been the result of incomplete understanding of Neptune's orbit, errors in measurement, problems with the telescopes used. They might have been explained by factors no one had considered, by things that had nothing to do with another planet at all. The entire justification for Pluto's discovery would crumble if that was the case. The entire reason for the search would dissolve. Scientists don't like finding out that the things they've built their careers on, the ideas they've invested in, the work they've done, might be mistaken. There's resistance to that kind of realization. It's uncomfortable. It's threatening. There's resistance in the scientific community, and there's resistance in individual scientists to admitting when they're wrong, or when something they've always accepted is actually false. But resistance or not, the data was there. The instruments were saying something that contradicted the old assumptions. The measurements were clear. It was time to look more carefully. It was time to question what had been accepted without serious challenge for nearly 50 years. Time to reconsider foundations that had seemed solid. The 1980s brought new measurements of Pluto pouring in from multiple observatories around the world. Radio observations. Infrared detection where different wavelengths of light could reveal things invisible light couldn't. Ultraviolet light analysis. Every technique that modern astronomy had developed and refined was being applied to understanding Pluto better. Every tool was aimed at extracting truth from that distant object. And with each technique, each new measurement, a clearer and more troubling picture emerged. Pluto was not just small. Pluto was tiny, genuinely, significantly tiny, considerably smaller than the Moon, smaller than many of the moons in the solar system, smaller than Mercury, smaller than Europa. It was a dwarf, a world that had been counted among the giants through a mix of luck and historical accident. A fortunate timing of discovery, but which didn't actually belong in that category. It had been miscategorized, promoted beyond its actual status, granted a position it hadn't earned. The mass estimates were revised downward repeatedly. Each new measurement and calculation drove the number lower, lower than before, lower than expected. Pluto was not Earth-like in mass, not even remotely close. It wasn't comparable to Earth or even to the Moon. It was a fraction, a small fraction, a tiny fraction of what had been thought decades earlier. The density calculations changed as a result. If Pluto was smaller, but still had substantial mass, it would have to be extraordinarily dense, made of rock and ice compressed to extreme pressures. But the spectroscopy didn't support that idea. The spectroscopy suggested something different. The light reflected from Pluto suggested a composition more consistent with ices than with dense rock. Methane ice, nitrogen ice, frozen nitrogen, Perhaps water ice as well. Frozen volatiles covering a rocky core. That composition made sense for something so far from the sun, where temperatures are so low that gases become solids, where methane freezes, where nitrogen freezes, where everything normal becomes ice. But a world made primarily of ice couldn't be as dense as the old calculations suggested, so the mass had to be lower, much lower, significantly lower than anyone had thought. The implications were becoming clear, though no one was quite ready to state them outright. Not yet. Not until they had to. Pluto wasn't a planet in any meaningful sense. Not really. It was something else, something smaller, something different, something that had been granted planetary status through a quirk of history and hadn't earned it through actual planetary characteristics or merits. But admitting this would mean admitting that the discovery had been misinterpreted. It would mean admitting that the planet found in 1930 wasn't actually a planet at all. It was a massive admission. It was professional embarrassment. It was questioning a decision that had been made decades earlier by respected astronomers, by Clyde Tombaugh, and others who had worked at Lowell Observatory. So people hedged. They published papers discussing Pluto's unusual characteristics. Many papers, many observations. They noted carefully that it didn't fit the pattern of the other planets. They acknowledged its strangeness, but they didn't quite say it outright. They danced around it. They didn't quite admit that the classification had been wrong. Not yet. Not until something else happened, something external. Something that would make the oddness of Pluto even more impossible to ignore or explain away. The universe was patient. The universe had time. And something was coming that would change everything. In 1978, an astronomer named James Christie was examining photographs of Pluto at the United States Naval Observatory. The work was routine in many ways. He was looking at the same kind of photographic plates that had been studied for decades. The technique was familiar, well established, understood. The equipment was refined but not revolutionary. What he noticed, though, changed everything. Changed how Pluto had to be understood. There was a bump on the edge of Pluto's image. A bulge. A slight distortion in the circular profile of what everyone had been looking at for so long. At first, it seemed like maybe a problem with the photograph. A flaw in the emulsion, a defect in the plate, dust or scratches or processing errors that had somehow made it into the image. He looked more carefully. He examined multiple plates taken at different times. The bump appeared on multiple images. Different images, different plates, taken on different nights, always there. It wasn't an artifact. It wasn't a flaw in the photography. It wasn't some random imperfection in the image. It was something real, something solid, something that existed independent of the photographic process. The bump moved over time. As different plates were taken on different dates, the position of the bump changed relative to Pluto. It rotated around Pluto. It circled the planet. It was orbiting. It was something in orbit around Pluto. It was a moon. Pluto had a moon. Astronomers had speculated about this possibility before, but there was no confirmation until now. Now there was. Now it was visible. Not a tiny moon either. Not some small rock barely held in orbit. A big moon. A substantial moon. A moon so large relative to Pluto that calling Pluto a planet and the moon a satellite seemed almost ridiculous, almost absurd, a misuse of language. The moon was named Charon, after the ferryman of the dead in Greek mythology, the figure who guided souls across the rivers of the underworld, which was appropriate and fitting given that Pluto was named for the god of the underworld, the god of death and the dead. The mythological naming was elegant. It fit the pattern, Charon for the moon of Pluto, and suddenly, the nature of Pluto's strangeness shifted completely. It wasn't just that Pluto was small and odd and didn't fit the pattern of the 8 classical planets. It wasn't just that the measurements didn't add up. It was that Pluto had a companion so large, so substantial, that it was almost a double system, a binary world. Two objects orbiting around a common center of gravity between them. Not one orbiting the other, but both orbiting a point in space between them. The size ratio was completely wrong for a standard planet and moon arrangement. In the Earth-Moon system, the traditional example, Earth is 81 times more massive than the Moon. The Moon orbits Earth. Earth is the dominant body. Earth is the planet. The Moon is the satellite. That's a proper planet and satellite relationship. That's how it's supposed to work. With Pluto and Charon, the ratio was completely different. Charon was perhaps half the diameter of Pluto, maybe slightly less. It was massive relative to Pluto. Genuinely massive, not a tiny moon orbiting a large planet, but two substantial bodies in orbital dance around each other, almost equal partners in their orbital relationship. Almost. The two objects were almost a pair dancing around each other. Almost equal. This was unlike any planet-moon system anywhere in the solar system. It was unique. It was odd. It had no precedent. It raised immediate questions about what Pluto really was, if it had such an unusual satellite, if the satellite was so large relative to the primary body, if Pluto was such a small object with unusual characteristics. How did it qualify as a planet? How could it meet the standard definition of a planet when no other planet had a moon like this? The discovery of Charon forced reconsideration in a way that the size measurements alone had not been able to. You could explain away size estimates. You could argue about density and composition. You could hedge. But you couldn't ignore a moon orbiting. You couldn't deny what was plainly visible in photographs. You couldn't pretend it wasn't there. And the existence of Charon meant that Pluto was even more anomalous than had been suspected. It wasn't just a small, odd world floating alone. It was a small, odd world with an unusually large moon. It was completely unlike any of the 8 classical planets. 8 planets had moons. But their moons were arranged in conventional ways. Earth had one moon. Mars had 2 small moons. Jupiter had many. The moons were small relative to the planets. The ratio was normal, but Pluto was different. One tiny, eccentric body had an enormous moon, an unusually large moon, a moon that almost looked like an equal partner. The pattern broke completely. The hierarchy that defined planetary systems was inverted with Pluto and Charon. Nothing else in the solar system worked like that. As the 80s progressed into the 90s, technology continued to improve constantly. Telescopes got better. Detectors became more sensitive. The Hubble Space Telescope was launched in 1990, though it had initial problems that were corrected by 1993. Problems with its mirror. Problems with its optical systems. But eventually, the problems were fixed. Repaired in space. Once operational and corrected, its capabilities were extraordinary. Genuinely extraordinary. It could see Pluto with unprecedented clarity. Clarity that ground-based telescopes had never achieved. It could measure its size more accurately than ever before. It could measure its composition in more detail. It could study Charon with detail and precision that ground-based telescopes could never achieve. And with Hubble, the picture became undeniable and uncomfortable. Pluto was smaller than the Moon, definitively smaller, smaller than 7 other moons in the solar system, smaller than Europa, smaller than Titan. It was a dwarf, genuinely, unambiguously tiny. The only reason it was counted as a planet at all was historical accident, pure historical accident. It had been discovered first. It had been discovered before we understood what else was out there. It had been named and counted as a planet for so long that tradition kept it in the planetary list, despite the fact that it didn't belong there by any rational standard. Tradition is powerful. It's hard to override. But tradition isn't science. At the same time, at the very same moment that astronomers were learning exactly how small Pluto was, something else was happening in the outer solar system, something that would make Pluto's status even more complicated. Astronomers were starting to find other objects beyond Neptune, other worlds. It began slowly, cautiously, a few discoveries here and there in the early 80s. Objects that were small, icy, and distant. Objects that resembled Pluto in fundamental ways. At first they were isolated findings, rare enough to be interesting but not surprising. But the discoveries multiplied. More objects were found, then more still. The rate of discovery increased. The numbers grew. A population of bodies was being revealed. A belt of icy worlds orbiting beyond Neptune. A ring of small worlds. A swarm of minor planets. This was not new theoretically. Gerard Kuiper had proposed the existence of such a belt decades earlier as a theoret. Eichel Place, where comets originated, where the bodies that eventually became comets came from. But proposing something theoretically is different from actually finding it. Finding it is different from knowing it's there. Observing something that you predicted without seeing it is one thing. Observing multiple examples and confirming the population is real, that's something else entirely. And the rate of discovery was accelerating dramatically. Every year brought new finds. Every year brought more objects. Larger objects appeared. Smaller objects were discovered. Objects with different orbital characteristics, different compositions. A diverse population was emerging from the darkness, slowly being revealed. And Pluto, which had seemed so unique and isolated, suddenly looked different. It looked wrong somehow. It looked like it didn't fit. It looked like one member of a population, not alone, not singular, not unique, but one of many, one example of a class of objects. The implications were staggering in scope. They were difficult to accept. If Pluto was just one of many, if it was one body among hundreds or thousands of similar bodies, then it couldn't remain categorized the same way as the 8 classical planets. Those 8 planets were unique in their regions. Each one dominated its orbital zone. There were no other planets like them, no competitors, no similar-sized rivals. But Pluto didn't dominate anything. It wasn't even the largest object in its region. Other bodies were being found that were comparable in size or larger, bigger than Pluto. Pluto was just the first one that had been discovered historically. It was prominent only because of timing. It had been noticed first. It was prominent in the Kuiper Belt only because it was nearby in discovery history, not because it was uniquely important in the solar system, not because it had any special status. The realization was slow to develop fully in the astronomical community, but the seeds were being planted. Seeds of doubt. Seeds of reconsideration. Pluto was not what everyone had thought it was. It had never been what everyone thought it was. The solar system had 9 planets, but perhaps it shouldn't. Perhaps the accounting was wrong. Perhaps the definition of what made something a planet had never been properly tested, had never been rigorously established, and now, faced with the reality of thousands of small icy bodies beyond Neptune, that definition was starting to matter, starting to become important, starting to demand answers from the astronomical community. Through the 1990s and into the early 2000s, the debate began to formulate more clearly, though not loudly or urgently at first. Not yet. Papers were published in scientific journals. Discussions happened in professional meetings and conferences. Arguments were made and counter-arguments offered about what Pluto was and what it should be called. Some astronomers suggested that perhaps Pluto should be reclassified. Perhaps it should be removed from the planetary list entirely. Perhaps it belonged with the Kuiper Belt objects instead, grouped with the small icy bodies that were its true neighbors in space and in composition. These astronomers made logical arguments. They pointed to the data. They pointed to the measurements. They pointed to the reality of thousands of similar bodies. But other astronomers defended Pluto's planetary status vigorously. They argued against reclassification. Yet the defenses were often weak. They didn't have strong arguments backed by data. They relied heavily on tradition, on history. They pointed to the historical significance of the discovery in 1930. They argued that Pluto had been counted as a planet for so long that changing that status now would be wrong. It would be revisionism. It would be disrespecting the work of Clyde Tombaugh and the astronomers at Lowell Observatory. But these arguments were unsatisfying even to those who made them, especially to those who made them. They knew they weren't addressing the real issue. Everyone could see the problem. Everyone in the astronomical community could recognize that Pluto didn't fit the pattern of the other 8 planets. Everyone understood that calling it a planet, while ignoring the thousands of similar but smaller objects being discovered, was arbitrary and illogical. It was inconsistent. It didn't make sense. Yet the question of what to do about it remained unanswered. There was no agreed-upon definition of what made something a planet, not an official one, not in writing, not even in the history books, just a loose understanding based on tradition and intuition and assumption. You knew a planet when you saw one. You could point to the 8 classical planets and everyone would agree. Those are obviously planets. But Pluto was the exception that broke all the rules. Pluto was the problem that exposed the lack of a real definition. Because once you started asking what actually defined a planet, once you admitted that the definition needed to be explicit and rigorous and based on science rather than history, you had to answer that question. You couldn't just say, well, so Pluto is a planet because we've been calling it one. That wasn't scientific. That wasn't based on evidence. That was just tradition masquerading as fact. That was history pretending to be science. The debate simmered throughout the 90s. It didn't come to a head. The astronomical community wasn't unified in opinion. Different people had different ideas about what should be done, different perspectives. Some wanted Pluto reclassified as something other than a planet. Others wanted to keep it as is, to preserve tradition and history. Some proposed new categories of objects, new classification systems. A few suggested that the entire planetary system needed to be reconsidered from the ground up. But there was no urgency to settle the question. Not yet. No real pressure. Pluto was still a planet. It was still counted officially. The solar system still had 9 planets in every textbook. Every educational material listed 9 planets. The debate was academic, interesting to specialists, but not pressing, not urgent. There was no deadline. There was no external force demanding resolution. No crisis. The question could wait. It could be debated and discussed for years, even decades, without anyone needing to make a final decision. Or so it seemed. But the universe had other plans. By 2005, the situation had changed dramatically, in ways that could no longer be ignored. The discovery rate of Kuiper Belt objects had accelerated exponentially. Telescopes had improved beyond what anyone in the 1930s could have imagined. Automated survey programs were scanning the sky continuously, methodically looking for faint moving objects. And they were finding them, constantly, hundreds every year, more every season. The population of the Kuiper Belt was being mapped out in unprecedented detail. New objects were being discovered almost monthly. And in 2005, something significant happened that changed everything. Astronomers discovered an object that was larger than Pluto, definitively undeniably larger. Its name was initially Eris, after the Greek goddess of discord, which was appropriate given the discord it would cause, though it was also catalogued with the designation 2073 EB 215, a designation that sounds like pure bureaucratic nonsense, but actually contains information encoded within it about when and where the object was discovered, the discovery program that found it, and details of its orbital characteristics. Eris was discovered to be about 27% larger in diameter than Pluto. It was significantly more distant from the Sun. It was definitely in the Kuiper Belt, part of that population of icy bodies, and it was undeniably real. It was there. It existed. It couldn't be explained away or ignored. The discovery of something larger than Pluto was the crisis that had been building silently for decades. This was the moment when the problem became impossible to ignore, impossible to put off any longer. If something larger than Pluto existed in the Kuiper Belt, if there was an object more massive and bigger than Pluto also out there, then the question had to be asked, had to be answered. What made Pluto a planet if this larger object wasn't a planet? What was the criterion that allowed Pluto into the planetary club but excluded Eris? There was no such criterion. There had never been one. There was no explicit rule that would justify keeping Pluto while rejecting Eris. And now, the absence of that definition was causing a problem that couldn't be swept aside anymore, couldn't be ignored, couldn't be avoided. The astronomical community couldn't keep Pluto as a planet while calling Eris something else entirely. That would be arbitrary. That would be indefensible. That would make no scientific sense. Either both were planets, or neither was. Those were the logical options. And if both were planets, then what about the other Kuiper Belt objects that were being discovered? If Eris was a planet and Pluto was a planet, then weren't all the other large icy bodies also planets by that same logic? By that same standard? Would the solar system suddenly have dozens of planets? Hundreds of planets? Thousands? The idea was absurd on its face, but it was the logical consequence of trying to defend Pluto's status in light of these new discoveries. You couldn't have it both ways. You couldn't cherry-pick which objects were planets and which weren't. Something had to give. Something fundamental had to change. The definition of a planet had to be established, finally and formally, with explicit criteria that could be applied consistently to all bodies in the solar system. The International Astronomical Union, the IAU, the international body responsible for astronomical nomenclature and classification and standards, faced enormous pressure, mounting pressure, pressure from all directions. Astronomers from around the world were asking questions loudly. The media was asking questions. The public was asking questions. People wanted to know answers. Was there a 10th planet? Had there always been a 10th planet and we just didn't know about it? Was Pluto still a planet? The pressure to answer these questions, to settle the debate once and for all, to provide clarity and certainty, became overwhelming. Impossible to resist. Something had to be decided. Something had to be formalized finally. The definition had been avoided for so long, pushed aside, put off indefinitely, that avoiding it any longer had become impossible. The moment of reckoning had arrived. In 2006, in late August, the International Astronomical Union held a special General Assembly meeting to resolve the question that had been building for so long. A resolution meeting, a formal convening to settle the matter. For the first time in the history of astronomy, in the entire history of categorizing the solar system, they sat down and formally, explicitly defined what a planet actually is. They had to decide on criteria, specific criteria. They had to be explicit about it. They couldn't rely on tradition or intuition. They had to create a definition that could be applied consistently across the entire solar system, a definition that would work now and in the future. The definition they came up with had 3 distinct parts. 3 requirements. First, a planet must orbit the Sun. Simple, straightforward, non-controversial. A planet orbits the Sun directly, not another body, not another planet or moon. It orbits the primary star. It orbits the Sun. That eliminates moons immediately. That eliminates satellites. Second, a planet must have enough mass to be rounded by gravity. In other words, it has to be large enough that its own gravity, the pull of its own mass, pulls it into a roughly spherical shape, a round shape. It has to be a world, not an asteroid or a small rock floating in space. It has to have achieved what's called hydrostatic equilibrium, where gravity has won the battle against the strength of the material and pulled everything into an equilibrium shape, pulled it into a sphere. This is a reasonable criterion, a sensible one. It separates small rocks and asteroids from actual worlds, actual planetary bodies. Third, and this is the critical part, the part that would change everything, a planet must have cleared its orbital neighborhood. It must be gravitationally dominant in its region. It must be the dominant gravitational presence. It must have cleared away other debris. It must be the primary body in its orbital zone. It can have moons. It can have small companions orbiting it. But it has to have cleared away the clutter. It has to have removed or assimilated, or ejected other bodies from its orbital neighborhood. It has to be alone in a meaningful sense. This third criterion is what killed Pluto's planetary status. It's what demoted it. Pluto doesn't clear its orbital neighborhood, not even remotely. The Kuiper Belt is absolutely full of objects, full of bodies, full of icy worlds. Pluto isn't gravitationally dominant. It doesn't dominate its orbital region. It shares its orbital region with thousands of other bodies, with potentially millions. It's one member of a population. It's a member of the Kuiper Belt population. It doesn't meet the third criterion. It fails the test. By this definition, by these explicit criteria, Pluto is not a planet. It's not a planet by any measure. It never was a planet, not really. It was misclassified for 76 years, from 1930 to 2006, but it was always something else. It was always a Kuiper Belt object. It was just the first one discovered. The IAU created a new category for objects like Pluto, objects that met the first 2 criteria but not the third. They called them dwarf planets, a new classification, a new category of objects, dwarf planets, bodies that orbit the Sun. They're large enough to be rounded by gravity. They have enough mass to form a spherical shape, but they don't dominate their orbital neighborhoods. They don't clear the space around them. They coexist with other similar objects. Pluto was classified as the prototype dwarf planet. It became the first official dwarf planet. It was the template. It was the example. It was still Pluto. It still existed. It still mattered. It still had significance. But it was no longer a planet. It had been demoted, stripped of the status it had held for most of a century, relegated to a new category alongside the thousands of other Kuiper Belt objects. The solar system went from 9 planets to 8. 8 classical planets. The traditional 8. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Those remained as planets. Pluto joined a new group, a growing group, a group of dwarf planets that would eventually include Eris and other Kuiper Belt objects, other objects that had been discovered. The classification was based on science, not history, based on clear, explicit, rigorous criteria, based on something that could be applied consistently to all objects. It made logical sense. It was defensible. It was rigorous, but it was also shocking in its implications. It was unexpected to the public. for people who had grown up learning about 9 planets, who had memorized the names as children, who had learned that Pluto was the smallest and coldest and most distant of all the planets. The reclassification was jarring. It was disorienting. It felt like something had been taken away. It felt like Pluto had been taken away, expelled from the family. It felt like something had been lost from the solar system. In reality, nothing had been lost. Nothing was missing. Pluto hadn't gone anywhere. It was still there in the cold darkness beyond Neptune. It hadn't changed. It hadn't moved. It hadn't ceased to exist. It hadn't become something different physically. Our understanding of it had changed. Our classification of it had changed. Our willingness to categorize it differently had changed. But the object itself was utterly unchanged. What had changed was our willingness to see it as it actually was, rather than as we had categorized it for so long. We had finally decided to look at reality instead of at tradition. But seeing something clearly is not the same as understanding it completely. Pluto was still mysterious. Pluto was still strange. Pluto was still a world that barely anyone understood in any depth. It was a dwarf planet now, reclassified, demoted from planetary status. But that didn't mean we knew what it was actually like. We had measurements, we had spectra, we had estimates and calculations and theories, but we didn't have direct observation. We didn't have close-range data. We didn't have spacecraft visiting the place to send back detailed information. We had never sent anything to Pluto. Not a single spacecraft had ever traveled there. Not one probe had ever carried instruments close enough to Pluto to give us real details, real pictures, real measurements that went beyond the theoretical. This was the situation in 2006 when the reclassification happened. The solar system had 8 planets now, and one dwarf planet, Pluto, that we barely understood at all. But there was a spacecraft already in development that would change that situation completely. A spacecraft that had been planned before the reclassification, before the debate about definitions, before Eris was discovered. A spacecraft that was designed to visit Pluto and study it in detail. To finally see what was there. To finally understand. It was a turning point. A moment when human exploration and scientific curiosity were about to be pointed at the most distant world we knew anything about. The idea for a mission to Pluto had been discussed for decades within the scientific community. Decades before it became a serious funded project. The challenges were enormous. The distance was incomprehensible. Pluto orbits at an average distance of about 3 billion miles from the Sun, maybe more. The numbers are so large they barely mean anything to human perception. 3 billion miles is further than the farthest point that any spacecraft had routinely traveled to at that time. It would take years to get there, years of travel through empty space, years of isolation, years of uncertainty. But the scientific interest was always there. Pluto was strange. Pluto was unique. Pluto deserved to be studied up close. So in the late 1990s, the concept was developed seriously. Not just dreaming about it, but actual mission planning. The Jet Propulsion Laboratory, JPL, which is the NASA center that designs and manages many of the solar system exploration missions, began working on designs for a Pluto orbiter mission, a spacecraft that would reach Pluto and go into orbit around it, stay there, study it carefully, return massive amounts of data over months or years. It was ambitious. It was risky. It was incredibly expensive. The estimate was billions of dollars, multiple billions. The cost of building an orbiter capable of reaching that distance and then slowing down enough to be captured by Pluto's gravity was staggering. But it was scientifically compelling. The best way to understand Pluto was to study it directly. to have instruments in close proximity, to take pictures from nearby, to measure temperature and composition and atmosphere and geology and everything else that made Pluto what it was. The plans were drawn up, designs were refined, concepts were developed. Engineers calculated trajectories and fuel requirements. They analyzed power systems and data transmission. They designed instruments and tested them. The work was detailed and demanding and required expertise in multiple fields. But then something else happened. Something that would change the entire approach. A simpler idea, a faster idea, a less expensive idea. What if instead of trying to orbit Pluto, the mission just flew by it? What if it came close, took pictures and measurements, and then continued on? A flyby mission instead of an orbital mission, much simpler, much faster to plan and build, much less expensive. Fewer instruments needed, smaller spacecraft required, lower fuel requirements. It would mean less time close to Pluto, fewer measurements, less comprehensive data. But it would be faster. It would be achievable sooner. It would reach Pluto before an orbital mission could be developed and funded. And there was another advantage. If the spacecraft was designed correctly, if the trajectory was calculated properly, it could continue past Pluto and explore the Kuiper Belt. It could study multiple objects. It could accomplish multiple science goals. The decision was made to pursue a flyby mission, a single close approach, detailed observations during the brief window when the spacecraft was closest, then continuing on into the outer solar system, continuing past Pluto into the Kuiper Belt if possible, studying other Kuiper Belt objects along the way if the spacecraft had enough fuel and remained functional. It was a compromise, but it was a pragmatic one. It was possible. It was doable. It could happen. It was revolutionary thinking for its time. It was bold. The mission was called New Horizons. The name said what the mission was supposed to do. Reach new horizons. Explore new places. Take humanity's vision further into the solar system than it had ever reached before. Travel to a place that no spacecraft had ever visited. See something that human instruments had never seen up close before. It was a mission of exploration in the truest sense. And the clock was ticking. Pluto's orbit is eccentric, irregular, not circular. It's pulled out of a neat round shape into an elongated orbit that brings it closer to the Sun sometimes and further away at other times. For much of the 20th century, Pluto was relatively close to the Sun. Not close in any conventional sense, but closer than its normal distance. In 2013, Pluto would reach aphelion, its farthest point from the Sun. After that, it would begin moving further away again, further into the outer solar system. If New Horizons didn't reach Pluto by roughly 2015 or so, the spacecraft would have to carry even more fuel to reach Pluto at a greater distance. It would take longer. It would be harder. It might not be possible at all with the spacecraft design that was being planned. The window was narrowing. There was urgency to the project. There was a deadline, not a hard deadline in some absolute sense, but a practical one. Launch had to happen within a certain time frame, or the mission would become much more difficult, much more expensive, possibly impossible. This created pressure within the project, pressure to move forward, pressure to build the spacecraft, pressure to test it thoroughly but not delay unnecessarily, pressure to launch as soon as it was ready. In 2006, and Pluto was reclassified as a dwarf planet. The New Horizons mission was well into development. It was not a concept anymore. It was real hardware being built, real instruments being constructed, real plans being finalized. Manufacturing had begun. Assembly was underway. Testing protocols were being established. The reclassification didn't change the scientific interest. If anything, it increased it. A dwarf planet that was the first of its kind to be studied up close. The prototype dwarf planet. The largest known member of a newly discovered population of objects. The need to understand Pluto became more important, not less, now that its actual status was clarified. New Horizons was a compact spacecraft. Not large, not massive. Much smaller than many of the planetary orbiters that NASA had sent to other worlds. It weighed about half a ton, less than 1,000 pounds. That's smaller and lighter than many cars. It needed to be small because it needed to be fast. Weight and spacecraft speed are inversely related. A lighter spacecraft can be accelerated to higher speeds with the same amount of rocket fuel. Speed was crucial. The farther the destination, the faster the spacecraft needed to travel, or the longer the journey would take. New Horizons was designed to be small and fast, efficient, streamlined for travel to the outer solar system. It carried instruments, but not an overwhelming number, not a complete scientific laboratory. Rather, a focused set of tools designed to study the specific things that scientists cared about most at Pluto. Cameras to take pictures, spectrometers to analyze light and composition in detail, magnetometer to study any magnet, IC field that Pluto might have, particle detectors to measure cosmic rays and solar wind, radio science instruments to study gravity and the interaction between the spacecraft and Pluto. Everything needed to do serious science, but nothing unnecessary. Nothing that would add weight. Nothing that would slow it down. Nothing that was merely nice to have when it wasn't essential. The power source was a radioisotope thermoelectric generator, an RTG, an isotope power system that generated electricity from heat. Solar panels wouldn't work this far from the sun. The sunlight is too weak, too little energy at that distance. RTGs use the heat from decaying plutonium to generate electricity reliably over many years. Plutonium, the element Pluto was named after, ironically. The spacecraft would be powered by the very element that named the dwarf planet it was sent to explore. It was a fitting cosmic coincidence. The launch was set for 2006. The same year that Pluto was reclassified, everything aligned. The spacecraft was ready or nearly ready. The rocket was ready. The launch window was approaching. January 2006 was targeted for launch. A specific date was set. Everything was building toward that moment. The spacecraft that would finally see Pluto up close was ready to leave Earth and begin its long journey into the outer solar system. It was ready to travel. It was ready to explore. It was ready to finally answer the question of what Pluto was really like. The launch happened on January 19th, 2006. January 19th. Just after the International Astronomical Union had made the decision to reclassify Pluto. Just as the world was adjusting to the idea that Pluto was no longer a planet, just as the confusion and debate about what Pluto actually was were reaching their peak. New Horizons lifted off. It rode an Atlas rocket out of Kennedy Space Center in Florida into the sky, into the upper atmosphere, into orbit, and from orbit it was accelerated toward escape velocity, accelerated toward a trajectory that would take it out of Earth orbit, out into the solar system, toward its distant destination. The rocket engines fired, the stages separated. The spacecraft was pushed higher and faster, faster than escape velocity. Fast, enough to never return to Earth, fast enough to leave Earth's gravity behind permanently. The spacecraft was gone. It was no longer on Earth. It was no longer under human control in any direct sense. It was on its own now, traveling through space, following its trajectory, following the path that had been plotted for it by its controllers on the ground before launch. Controllers watched the data stream back to Earth, confirming that everything was working. The navigation was correct. The separation had occurred as planned. The spacecraft was performing. Once it was beyond Earth's influence, there was no way to call it back. There was no way to retrieve it if something went wrong. There was no abort option. The mission was committed. The die was cast. The spacecraft was going to do what it was going to do. New Horizons was launched on a trajectory that would take it to Jupiter first. The spacecraft couldn't reach Pluto directly. It wasn't fast enough. It couldn't build up enough speed on its own to reach Pluto in a reasonable time frame. But Jupiter was in the way. Jupiter and its immense gravity. If New Horizons approached Jupiter correctly, if it used a gravity assist maneuver, it could use Jupiter's gravity to accelerate, like a slingshot effect. A carefully calculated approach to Jupiter would swing the spacecraft around the planet and speed it up. Add velocity without burning fuel. This was the trick of space exploration, using the gravity of massive bodies to accelerate spacecraft, saving fuel by using the natural movements of planets, using physics to do the work that propellant would otherwise have to do. New Horizons would approach Jupiter, use it for a gravity assist, and then continue on with additional velocity toward the outer solar system. It would continue toward Pluto. It would fly past Jupiter close enough to be accelerated, but not so close as to be damaged by radii. Tie-in in Jupiter's magnetosphere. It was a precisely calculated maneuver. A maneuver that had been used many times before, but never got less risky. But the journey wouldn't be quick, not quick in any human sense. The distance was vast. The travel time would be measured in years, plural, more than 1 year, multiple years, nearly a decade from launch to arrival, 9 years, roughly, 9 years of travel through empty space, 9 years where the spacecraft would be slowly moving away from the Sun, moving toward Pluto, moving toward a destination that wouldn't be reached until the spacecraft was nearly ancient by spacecraft standards, nearly obsolete. But that was acceptable. That was expected. The journey to Pluto had always been understood as a long journey, a journey that would take years. Scientists would have to be patient. The space agencies funding the mission would have to be patient. The public would have to be patient. This wasn't a quick trip. This wasn't something that would happen next week or next month or next year. This was a long-term commitment, a commitment that stretched across years, a commitment that tested whether the public and funding agencies would remain interested in a mission to a place that most people had thought was a planet until very recently, and which was now being redefined as something entirely different. The journey began. New Horizons accelerated past Jupiter in 2007, got its gravity assist, increased its velocity significantly, changed its trajectory, began the long approach to Pluto. It would take another 8 years to reach its destination, 8 years from the Jupiter encounter until the moment of closest approach to Pluto, 8 years of traveling through empty space, 8 years of silence in terms of major events. The spacecraft was working, its instruments were functioning, it was collecting data about the environment it was passing through. Cosmic ray detectors measured radiation, particle detectors measured solar wind, temperature sensors tracked thermal conditions. But there were no planetary encounters, no dramatic moments, no major news updates, just steady travel, just the slow approach toward a destination that was still years away. The spacecraft was doing its job. The mission was proceeding, but it was doing so in relative obscurity. The public had moved on. The media had moved on. New Horizons was traveling, but nobody was watching anymore. The years passed. Time moved forward. The world changed. New administrations came to power. Political situations shifted. Technology advanced. New discoveries were made. Life on Earth continued. But New Horizons kept traveling, kept approaching its destination. It was like a very slow pendulum swinging, or a very slow boat moving through an endless ocean. The journey was monotonous by necessity. There were no events, there were no major milestones, just the steady passage of time and the steady approach of distance. The world's attention span didn't extend to distant spacecraft traveling through empty space. Other news dominated headlines. Other events captured imaginations. New Horizons was doing its job, but it was doing it invisibly, quietly, without fanfare, without dramatic moments. Just the slow, steady progression toward a destination that still seemed impossibly far away. Gradually, as the years wore on, as the spacecraft got closer and closer to Pluto, as the scheduled encounter date began to approach, the excitement began to build. Scientists who had been waiting for this moment for years, who had planned for it, who had designed instruments specifically for this encounter, began to anticipate what they would see. They began to think about it more intensely. What would Pluto actually look like? What would it reveal? Scientists had hypotheses based on all the data that had been collected from Earth. Models had been made. Theories had been developed. But hypotheses aren't the same as reality. Reality would be revealed only when the spacecraft arrived. Only when its instruments could see Pluto up close. Only when the measurements could be made. All the theories would be tested against observed fact. All the assumptions would be challenged by reality. Some of the hypotheses were likely correct. Some were probably wrong. That was how science worked. Prediction followed by observation, followed by refinement of understanding. The process was slow, but it was reliable. It moved toward truth incrementally. The public began to pay attention again. News stories started to appear about the approaching encounter. People who had learned about Pluto being reclassified as a dwarf planet began to wonder what it actually looked like. What would we see when we finally got there? What would Pluto reveal about itself? What would be there that surprised us? What would look different from what everyone expected? The anticipation grew, not frantic anticipation, not urgent excitement, but a gradual building of interest, a growing sense that something important was about to happen, something we had never seen before, a place we had never studied directly, a world that was about to reveal itself to humanity, a world that had been orbiting the sun since the beginning of the solar system, but had never been visited, never been observed directly, never been known anything other than theoretically. Now, for the first time, that was about to change. The waiting was about to end. Decades of planning, years of travel, and finally, the moment was approaching. The flyby was coming. The closest approach was getting near. The instruments would finally see Pluto clearly. The data would finally flow back to Earth. The universe would finally show us what it had been hiding in the outer solar system. The wait was almost over. The anticipation built month by month, week by week, day by day. The countdown was real now. The moment was not years away anymore. It was months away, then weeks, then days. The entire world was starting to focus on this distant encounter. Scientists were excited. The media was preparing. The public was curious. Everyone was waiting. The approach to Pluto accelerated. The final phase of the journey. The distance closed from millions of miles to thousands of miles to hundreds of miles. The date approached. July 2015. July. The height of summer in the northern hemisphere. The peak of the year when heat and sun dominate the climate. And in July, on a specific date in July, New Horizons would have its moment of closest approach to Pluto. The entire mission hinged on this moment. Everything else was preamble. Everything else was preparation. This moment, this brief window of time when the spacecraft would be at its closest point to Pluto, would determine the entire success or failure of the mission. The closest approach would happen on July 14, 2015. 9 years and nearly 6 months after launch. 9 years since the spacecraft had left Earth orbit. 9 years of travel through the solar system. And on that date, the spacecraft would reach its closest point to Pluto. It wouldn't go into orbit. It wouldn't stay. It would pass by at high speed. Approach, pass at closest distance, and then continue past and away. The entire encounter would be brief. The closest approach would last for only a few minutes. A few minutes to collect the most detailed data. A few minutes to take the closest pictures. A few minutes to study an entire world that human instruments had never observed in detail before. It was a slim window. It was a narrow opportunity, but it was real. It was going to happen. Scientists and engineers and NASA officials had all been preparing for this moment for years. The instruments had been tested and tested again. The software had been verified and verified again. The sequences that would control what the spacecraft did at closest approach had been programmed and reprogrammed, hammered and checked for errors. The mission timeline had been planned and replanned to account for every contingency. Everything was ready. Everything was prepared. The countdown was on. Pluto was about to be seen. New Horizons was about to reveal what had been invisible to human science for so long. The moment was approaching. On Earth, in control centers, scientists monitored the spacecraft. Johns Hopkins University Applied Physics Laboratory in Maryland was the mission control center. Scientists and engineers gathered there. They tracked the spacecraft's location. They verified its health. They confirmed its systems were operating. They prepared for the moment when it would reach its destination. The anticipation was almost unbearable. They had waited so long. So very long. For decades. For years. And now the time was finally here. The moment was finally arriving. Pluto was about to be studied. Pluto was about to reveal itself. The unknown was about to become known. And nothing, not the distance, not the years of waiting, not the enormous challenge of the mission, could diminish the moment when it finally arrived. When closest approach happened, it wasn't dramatic in the traditional sense. There were no explosions. There were no sudden revelations broadcast live to the world. It was quiet. It was scientific. It was methodical. The spacecraft, moving at a high speed through space, passed by Pluto at a distance of about 7,000 miles. 7,000 miles. That's roughly the width of the United States multiple times over. It's a vast distance in human terms. But for a spacecraft in space, for a small probe visiting a distant world for the very first time, it was close. It was near enough. It was near enough for the instruments to collect detailed information. Near enough for the cameras to take clear pictures. Near enough for the spectrometers to analyze composition and material properties. Near enough for everything the scientists wanted to know, and more than they had dared hope to discover. The spacecraft took pictures. Lots of pictures. Hundreds of them. Thousands, actually. Images of Pluto's surface taken from various angles and distances as the spacecraft approached, passed, and receded from the dwarf planet. Images showing details that had never been visible before. Images revealing what was actually there in the cold darkness of the outer solar system. The pictures streamed down to Earth, radioed back across billions of miles of empty space. The signal traveled at the speed of light but still took time to cover that vast distance. It took more than 4 hours for the images to reach Earth. More than 4 hours of waiting, while the data traveled through the vacuum of space. Hours of anticipation building, and when the first images arrived, when the first pictures of Pluto's surface were received and displayed on screens in control centers and laboratories and offices around the world, the reaction was immediate and undeniable. Surprise, astonishment, wonder, excitement beyond what anyone had fully anticipated. What people saw was not what they had expected, not what the theories had predicted, not what the models had suggested based on distant observations. Pluto was not a featureless, smooth, icy ball. It was not a boring, homogeneous world without variation. It was complex. It was geologically diverse. It was strange and unexpected. It was beautiful in ways that shocked everyone. It showed features that didn't fit the models that had been built based on theoretical understanding. Mountains made of water ice, deep valleys and canyons cutting through the landscape, vast plains of frozen nitrogen and other ices, different regions showing different compositions and colors, different textures and surface patterns, different colors and contrasts that revealed underlying geology. The pictures told a story of a world that was far more complicated than anyone had anticipated, far more interesting than anyone's imagination had dared suggest. A world that was geologically active, or at least a world that had been active in its relatively recent past. A world that was not dead and frozen and simple, but genuinely complex and interesting and full of features that demanded explanation and further study. Pluto had revealed itself. For the first time, humanity saw this distant world not as a point of light in the darkness, not as an abstract concept discussed in textbooks, not as merely a classification problem or an astronomical curiosity, but as a real place, a real world with real geology, real features, real complexity, real beauty that transcended the expectations of scientists and the public alike. The revelation started immediately. The first few images showed a landscape of striking contrast. A region on Pluto called the Sputnik Planitia, a vast plain roughly the size of a continent, appeared to be made of frozen nitrogen. Frozen nitrogen was not expected to cover such a large area. Nitrogen ice is relatively soft, relatively fragile compared to water ice or rock. It should have been worn down by impacts and by sublimation, the process where ice turns directly into gas without becoming liquid. Over billions of years, a plain of nitrogen ice should have been smoothed down or destroyed entirely. But here it was, fresh looking recent, looking maintained somehow, looking like it was actively resurfacing itself continuously. The plains were smooth in some areas and featured hexagonal patterns in others. Patterns that suggested convection cells, places where warmer material from below was rising and cooler material was sinking in a continuous cycle. Convection in a frozen world. Heat from the interior pushing through the surface. This meant Pluto was not completely frozen through and through. There was heat inside. There was geological activity. There was motion and change happening. Pluto was not dead. It was not the frozen, inert, geologically boring world that everyone had imagined based on theoretical understanding. It was alive in some sense. It was dynamic. It was changing. It was flowing like a glacier, like flowing material that moved across the surface over the course of time. The nitrogen plains were not static and unchanging. They were active. Around, the edges of the nitrogen plains were mountains made of water ice. Water ice mountains. Real mountains with steep slopes and dramatic peaks rising sharply. Mountains rising kilometers above the surrounding terrain. Mountains that were sharp and relatively young-looking, not worn down and eroded by time. Mountains that looked like they had been built recently on geological timescales. They were impressive features. They were dramatic and commanding. They dominated regions of the surface completely. They showed that Pluto had more complexity in its geology than anyone had thought possible. Different regions had different compositions, different materials, different geological histories and stories written in rock and ice. The diversity was striking. The images revealed not just what was there, but that what was there was far more complicated than anyone had expected. More interesting, more deserving of serious scientific attention, more fascinating than anyone's imagination had allowed. And the data kept coming. Measurements from the spectrometers analyzing what Pluto's surface was made of, confirming the presence of nitrogen ice, methane ice, water ice, carbon monoxide ice, and other compounds, showing how those materials were distributed across the landscape, showing regional variations in composition, temperature measurements taken by infrared instruments revealing thermal patterns, measurements attempting to detect any magnetic field, data about particles and radiation in the near Pluto environment. All of it combining to paint a picture of a world that was genuinely strange, genuinely interesting, genuinely surprising in its complexity. Pluto had spent so long being known only as the small, distant, mysterious world at the edge of the solar system. Known mostly for being strange and different. Known mostly because it was an anomaly that didn't fit the pattern. But now, finally, with actual detailed observation, it was becoming known for what it actually was. A complex world. A world with its own geology. A world with its own story. A world that was far more interesting than anyone had imagined before the data arrived. The reclassification as a dwarf planet had answered a question about what Pluto should be called, about how to categorize it, about where it fit in the taxonomy of the solar system, about how to define planets versus dwarf planets in a way that made logical sense. But the New Horizons encounter answered a completely different set of questions. It answered the question about what Pluto actually was, what it was like, what it contained, what its history was, what it was made of. The two were separate but related. The reclassification had forced scientists to think about Pluto differently. The encounter had forced them to understand Pluto differently, and the two together painted a picture of a world that deserved its own category, not because of some taxonomy issue, but because it was genuinely unique, genuinely different from the classical planets, genuinely belonging to a class of objects that were abundant in the outer solar system, objects that had been hidden, mostly invisible, mostly unknown, until now. Objects that were starting to reveal themselves, objects that were starting to be understood. Pluto was the first of these objects to be studied in detail, but it would not be the last. The New Horizons spacecraft continued past Pluto, continued into the Kuiper Belt, continued on its journey to explore the outer reaches of the solar system. Other spacecraft would follow. Other missions would visit these distant worlds. Other revelations would come in the years ahead. But Pluto, in that moment, had been seen. Pluto had been known. Pluto had revealed itself to humanity, and in doing so, it had opened a window onto an entire population of worlds that had been hidden in the darkness of the outer solar system for all of human history. The Sputnik Planitia was the most immediate puzzle. This vast plain of frozen nitrogen stretched across thousands of kilometers, smooth in some areas and intricately patterned in others. Scientists stared at the images trying to understand what they were seeing. What they were looking at made no sense with the existing models. Nitrogen is volatile. Nitrogen is unstable over geological time. Nitrogen should not survive exposed on the surface for billions of years. It should sublimate. It should turn directly from solid ice into gas and escape into the thin atmosphere that Pluto had somehow managed to maintain. But here it was, fresh-looking, young-looking, actively renewing itself before the spacecraft's instruments. The texture suggested active modification happening continuously. The appearance suggested ongoing processes reshaping the landscape. The entire plane spoke of something that was still happening, still moving, still reshaping the surface beneath it. Nitrogen was being deposited. Nitrogen was being removed. The balance was shifting. The material was flowing. The nitrogen planes were not static features, frozen in place at some point in the past. They were active. They were current. They were participating in Pluto's ongoing geology. The patterns within the planes told a story that geologists struggled to interpret. Hexagonal cells arranged in regular grids like the surface of a honeycomb. Like basalt formations on Earth, where lava cools and cracks into columns. Like tile flooring arranged in perfect geometry. Repeating hexagons. Regular spacing. Natural geometric patterns. These patterns form when fluid material beneath the surface is heated from below and rises upward. Heat drives motion. Warmer material expands and becomes less dense. Less dense material rises. It moves upward through the overlying material. Cooler material at the surface becomes denser and sinks downward to replace the rising material. The result is convection cells. Rolling motion of material in a circular pattern. Upwelling in the middle of a cell. Downwelling at the edges. The pattern repeats endlessly. The geometry is almost mathematical in its precision. Hexagons fill space efficiently. Hexagons optimize the surface area to volume ratio. Nature discovers these patterns repeatedly. Hexagons appear in geology when convection happens. Hexagons appear in biology in honeycomb structures. The pattern is efficient. The pattern is natural. The pattern reveals something about the underlying physics. But nitrogen ice should not convect. It should not flow. It should not move like a fluid over geological timescales. Ice is solid. Ice is brittle. Ice should crack and break and become damaged with time. And yet it appeared to be doing exactly that. Convecting like water in a pot on a stove. Moving like hot material rising and cool material falling. Behaving like a fluid despite being frozen. Models had to be revised. Theories had to be reconsidered. Assumptions had to be questioned. The data suggested that despite temperatures reaching -390 degrees Fahrenheit, or colder, the nitrogen ice was moving. Moving continuously. Moving persistently. It was flowing like a glacier flows, slowly, inexorably, reshaping itself continuously over geological time. Something was keeping it warm enough to move. Something in Pluto's interior was providing energy to the surface. Something was driving geological activity on a world that was supposed to be dead, frozen, geologically inert. The Sputnik Planitia became synonymous with mystery. It became the symbol of everything that Pluto was teaching us about how small, distant, cold worlds could still be geologically active. Around the borders of the nitrogen plains were mountains made of water ice that seemed to float on the surface. This was not metaphorical poetry. This was literal geology. The mountains actually appeared to float. Water ice is denser than nitrogen ice. Water ice is heavier, much heavier, more massive. The density difference was significant. Blocks of water ice should sink into nitrogen ice the way icebergs sink into water if the water is warm enough to allow sinking. That was how buoyancy worked. Denser objects sank. Less dense objects floated. But here, the mountains were resting on top of the nitrogen plains. Apparently not sinking. Apparently held up by the very material they should have been sinking into. The water ice mountains rose thousands of meters above the surrounding nitrogen plains. Sharp peaks, dramatic slopes, real topographic prominence. visible from space, photographed clearly. Yet they floated. They were supported. They were held up. This was impossible according to the models. This was illogical according to the theories. This was exactly what the observation showed, what the data revealed. This suggested that the nitrogen planes were stronger, more rigid than expected, stronger than models suggested nitrogen should be at Pluto's temperatures, stronger than the theory predicted, or that something was supporting the mountains from below, some process, some mechanism, some force, or that the entire picture of how Pluto's surface worked was fundamentally different from what the simple models had suggested before the encounter. The mountains were massive features, not small peaks, not minor topography, serious topography, important features, rising so high that they should have crushed down under their own weight into the softer nitrogen beneath them. Gravity should have pulled them down. Weight should have forced them through the softer material. But they didn't sink. They sat there, apparently stable, apparently comfortable, supported by material that should have allowed them to sink. This was a puzzle. This demanded explanation. This forced geologists to think differently about how ice behaved at these temperatures and pressures. This showed that Pluto still had surprises waiting. Other regions showed evidence of past geological activity spread across the surface. There were impact craters, like on every moon and planet, numerous and varied. But they were different from what was expected. On many worlds, impact craters are surrounded by rough, chaotic terrain ejected from the impact site. Ejector blankets, impact debris scattered across the surface, rocky desolation around each crater. On Pluto, some craters had different patterns entirely. Some had smooth-walled depressions surrounding them, smooth walls, rounded features, soft topography. Some had evidence of material flowing over the crater rims, flowing past the impact site, covering it, erasing it, like water flowing over a rock, like lava flowing across a landscape. The geology was not simple. The geology was not straightforward. The geology was telling a complicated story about a world that had evolved over time, that had changed, that had experienced different types of geological processes working at different times in different ways. There were canyons and valleys cutting through the surface, massive canyons, deep valleys that suggested ancient water ice flowing like rivers carving through rock on Earth, flowing slowly, persistently, reshaping the landscape over time. Water ice does not flow easily at Pluto's temperatures, not like liquid water flows on Earth. But under pressure, over millions of years, ice can behave plastically. It can deform, it can move, it can flow, slowly. But it can flow. These canyons might have been carved by such flowing ice, by glaciers of water ice, moving across the surface, cutting through the terrain, creating deep valleys, creating dramatic topography, creating evidence of past activity, canyons that implied extension and stretching of the surface, pulling apart, tearing, creating rifts and valleys. If the surface was being stretched, if it was being pulled apart, that meant internal pressure was pushing outward from below. Pressure from heat inside, pressure from expansion of interior material, pressure from movement inside. That meant heat and motion inside. That meant there was something happening beneath the surface, something active, something dynamic. That meant Pluto was not cold and dead. It was dynamic. It was active. It was alive in the sense that geology meant alive. Alive meant changing. Alive meant responding to internal forces. Alive meant not static and unchanging, but evolving and transforming. The diversity of features was striking beyond words. Different regions had completely different characteristics. One region appeared cratered and old and relatively unchanging by recent standards. Another appeared smooth and young and actively resurfacing, suggesting ongoing processes. Some areas had distinctive colors suggesting different compositions or different surface processes. Some regions were light. Some were dark. Some had layers. Some had patterns. The geological story was not uniform. It was regional, varied, complex. Different parts of Pluto had experienced different histories. Different parts had evolved differently over time. Different parts were telling different stories. The entire world was a puzzle waiting to be solved, a jigsaw with pieces that did not fit the expected picture at all. The atmosphere was its own mystery entirely. Pluto had an atmosphere. This alone was surprising in the way that fundamental facts can be surprising. The gravity was weak. Pluto's gravity was not strong enough to hold an atmosphere, or so the theory said. The temperature was extreme. Pluto's temperature was not warm enough to maintain atmospheric gases, or so the logic suggested. The expectation was that any atmosphere would have escaped into space billions of years ago. The solar wind would have stripped it away. The thermal energy of the molecules would have been enough for them to achieve escape velocity and disappear into the void. Any atmospheric molecules would have achieved sufficient speed to escape Pluto's weak gravitational field and simply left forever. But radio science measurements conducted during the encounter showed that Pluto had an atmosphere. The data was unambiguous. The radio signals from the spacecraft changed as they passed through the atmosphere. The atmosphere refracted the radio waves. The refraction could be measured. The magnitude of the refraction revealed the density of the atmosphere. The atmospheric pressure could be calculated. It was thin, incredibly thin, many millions of times less dense than Earth's atmosphere. But it was there. It was real. It was measurable. It was composed primarily of nitrogen with traces of methane and carbon monoxide, frozen nitrogen normally. But at the extremely thin pressures of Pluto's atmosphere, and at the slightly warmer temperatures where Pluto was in its orbit, some nitrogen existed as gas. Gaseous nitrogen, floating above the surface, rising upward, forming layers. It was strange that it existed at all. How was it maintained? How did it persist when all the logic suggested it should be gone? One possibility was that the atmosphere was temporary. Temporary on a geological timescale, but perhaps stable on a human timescale. Pluto was at a point in its orbit where it was relatively close to the Sun, not close in any normal sense, still 3 billion miles away, still receiving almost no heat, but close compared to its more distant orbital positions. As Pluto moved farther from the Sun in the years and decades ahead, the atmosphere would freeze out. Gases would condense into ice. The atmosphere would freeze onto the surface as solid nitrogen. The atmosphere would disappear. The surface would solidify further. Things would change dramatically. The world would transform. But for now, in this era, there was an atmosphere. There was something that could be called wind. Wind pushing across the nitrogen plains. Wind carrying ice crystals. Wind at the edge of the solar system. There was something that could be called weather. Weather patterns. Atmospheric circulation. Pressure systems. Pluto had weather at the edge of the solar system. The implications were staggering. The atmosphere extended upward into hazes and layers that could be photographed from distance. Visible layers of atmospheric structure. The hazes suggested that particles in the upper atmosphere were being irradiated by ultraviolet light from the Sun. Even at such distance, the Sun's ultraviolet radiation was strong enough to affect the chemistry. The ultraviolet was transforming the simple nitrogen molecules into more complex organic compounds, breaking bonds, creating new bonds, changing the chemistry. These compounds were polymerizing, linking together, forming complex chains, molecules becoming larger, becoming more complex, becoming more interesting chemically. The result was organic haze. Complex chemistry happening in an atmosphere billions of miles from the sun, happening in the cold and dark, happening in isolation from Earth and life and everything familiar. The haze was visible in the images. It formed layers visible from space. It formed patterns that revealed atmospheric structure. It suggested that chemistry was happening actively, that Pluto's atmosphere was not inert. It was not static. It was participating in ongoing chemical processes that transformed matter at the molecular level, creating new compounds, creating organic chemistry. The haze also settled onto the surface in some places. Particles falling, condensing, depositing. In the polar regions, there appeared to be deposits of reddish material, distinctive color, visible in the spectroscopic data. This was not water ice. This was organic material, complex organic compounds, Tholins perhaps, chemicals created by ultraviolet light striking simple organic molecules. This was where the atmospheric chemistry was depositing its products. This was where the transformation of simple gases into complex molecules was leaving its mark on the landscape, building layers, creating deposits, coloring the world. The atmosphere was not just something that existed passively. It was doing something. It was participating in geology. It was affecting the surface. It was driving processes that were shaping the world. The thinness of the atmosphere did not diminish its importance. It did not make it irrelevant. It made it active and dynamic in its thinness. It made every molecule important. It made every interaction between atmosphere and surface significant on a planetary scale. The atmosphere was working. Then there was Charon. Charon was Pluto's moon. Not a small moon orbiting a large planet. Not a minor satellite. A large moon. So large that it was almost possible to think of Pluto and Charon as a binary system. Two objects orbiting each other, rather than one object and a satellite. Charon was more than half the diameter of Pluto. It was a significant world in its own right. A world that deserved study. A world that had its own story to tell. If Pluto was strange, Charon was equally strange in different ways. Charon's surface was covered with craters. Impact craters from countless collisions with smaller objects over billions of years. The scars of impact written across the surface. Evidence of a violent history shared with every other moon and asteroid in the solar system. But Charon also had other features that demanded explanation. There was a massive canyon system cutting across the equator. A canyon so large and so deep that it dwarfed anything comparable on Earth or other planets. The Grand Canyon was a modest feature in comparison. The canyon stretched for thousands of kilometers. The walls dropped thousands of meters. Sheer faces. Dramatic topography. The canyon was apparently formed by extension, by the moon being pulled apart, by interior processes causing the surface to break and crack and subside. The surface stretched. The crust fractured. Material sank in the middle. A rift valley formed. Evidence of internal stress. Evidence that the moon had been active once. Charon's northern hemisphere appeared smoother and newer than its southern hemisphere. The northern regions had fewer craters, many fewer. The scarring was less severe. They had been resurfaced somehow, completely resurfaced. They had been geologically renewed. The southern regions were old and battered and heavily cratered, showing the accumulated damage of billions of years of impact. Covered in scars, marked by time, the two hemispheres told different stories written in rock and ice and shadow. One region spoke of recent activity, One region spoke of ancient history. One was young. One was old. One appeared fresh. One appeared weathered. But they were on the same moon. This required explanation. This demanded understanding that could account for such different regions on a single body. The most likely explanation involved internal heat. If there had been a source of heat in Charon's interior, if the moon had been warmer in its past, if geological activity had been more vigorous in earlier times, then the northern hemisphere might have been heated and softened and resurfaced by volcanic activity or cryovolcanism. Water ice would have flowed. The ice would have moved like rock flows. The surface would have been renewed. New material would have covered the old. The craters would have been buried and erased. The old geology would have been hidden beneath the new. But as the moon cooled over billions of years, the activity would have diminished. The heat source would have been exhausted. Eventually, the activity would have stopped completely. The internal engine would have turned off. The southern hemisphere, perhaps always in shadow or insulated by distance from the heat source, would have remained unchanged, unchanging, inert, accumulating craters as impacts happened, building up damage, marking time with impact scars, telling the story of ancient times preserved in impact craters and ancient topography. Charon was only a few hundred kilometers in diameter. It was small on any planetary scale, smaller than Earth's moon, smaller than most moons. But it had a complex geological history. It had evolved. It had changed. It had been active. It had experienced geological processes. The relationship between Pluto and Charon added complexity to the system. They orbited each other with a period of several Earth days, 6 Earth days approximately. They were locked together tidally, always showing the same face to each other, always presenting the same hemisphere toward their companion. This was not an accident. This was a consequence of orbital mechanics. The gravitational interaction between them had evolved their orbits until they synchronized. They faced each other. They watched each other eternally. This meant that the tidal forces between them were immense. The gravitational pull of one on the other created stresses within the bodies, stretching, pulling, creating internal pressure. It created heating through friction. The internal rocks and ices would move slightly relative to each other. The movement created friction. Friction created heat. Small amounts of heat, but accumulated over billions of years, enough heat to drive geological activity. It created motion. It created the energy that drove geological activity in both bodies. If Pluto and Charon had been alone, isolated from each other, both would probably be completely frozen and geologically dead. Cold, inert, unchanging. But together, their interaction, their mutual gravitational influence, created energy, created warmth, created the potential for activity and change that would not be possible if they were all one. The compositional data was equally mysterious in what it revealed and concealed. Spectrometers had analyzed the light reflected from different regions of Pluto and Chiron and identified the chemical composition. The instruments spread the light into spectra, rainbows of reflected light. Different materials reflected different wavelengths of light with different intensities. By analyzing these patterns, scientists could determine what materials were present. Water ice was abundant, as expected. It was there, covering significant areas. Water ice made sense. Water was common in the solar system. Ice was the natural state at these temperatures. But water ice is not the only thing there, not the only material, not the only composition. Nitrogen ice dominated in some regions, covering N-tie plains, forming major features. Methane ice appeared in others, creating distinct regions, creating compositional boundaries. Carbon monoxide ice was present, but less abundant. Smaller deposits, more localized. These materials formed different types of terrain. They had different colors. Red ice looked different from white ice. Different compositions produced different appearances. They had different reflectivities. Some materials were bright enough to reflect most of the sunlight that reached them. Some were dark enough to absorb most of the light, dark enough to look almost black in the images. Some materials absorbed light in particular wavelengths. Some bounced it back. The reflectivity patterns revealed composition. They had different hardnesses. Some ices were soft enough to deform under slight pressure. Some were hard enough to resist deformation. Some brittle, prone to cracking and shattering. The hardness mattered. It determined how the surface would respond to impacts, how it would behave when stretched, how it would interact with the environment. They had different densities. Some materials were heavier, denser, more compressed. Some lighter, less dense, more buoyant. The density differences affected how materials would settle and arrange themselves. They behaved differently under the conditions present on Pluto. At these temperatures and pressures, ice did not behave the way it did on Earth. The laws of physics were the same, but the parameters were so different that the results were often unexpected. Ice had different properties, Ds, afferent characteristics, different ways of moving and changing than it did at the warmer temperatures of Earth. The boundaries between different compositional regions were sometimes sharp, sometimes gradual, sometimes overlapping and mixing in ways that suggested ongoing processes, active mixing, movement, change. The distributions did not follow simple patterns. One region might be pure nitrogen ice, adjacent to another region with different composition. An adjacent region might be a mixture of nitrogen and methane. The two substances mix together, creating intermediate compositions. Another region might be predominantly water ice, with methane deposits in particular locations, patches of methane on a background of water ice. The complexity suggested a complex history. Different material, S had been deposited at different times, different eras, different geological epochs. Different materials had been exposed through erosion or impact cratering. Buried materials brought to the surface, old materials revealed by impact. Different materials might have migrated across the surface over time as they sublimated in warm spots and recondensed in cooler regions, moving, traveling, redistributing. The reddish material visible in the polar regions was particularly intriguing. Distinctive coloration, visible in the images. This was organic material, complex organic compounds, carbon compounds, not simple hydrocarbons, complex molecules. How had they formed? One possibility was that they were created by ultraviolet light from the sun hitting simpler organic molecules. Even at this DISTA NC, the ultraviolet broke the molecules apart and caused new bonds to form, breaking and creating, destroying and building. New, larger, more complex molecules emerged from the process. This happened in the thin atmosphere, creating hazes, creating particles, visible haze. This happened on the surface, creating deposits, building layers, accumulating over time. Over billions of years, simple organic material could be transformed into complex organic compounds. Complex chemistry happening slowly, happening over vast timescales. The reddish appearance suggested that these compounds contained what chemists called aromatic rings, benzene-like structures of carbon atoms that absorb visible light in particular ways. Complex ring structures, carbon atoms linked in geometric patterns. These structures had distinctive optical properties. They absorbed certain colors of light. They reflected others. This gave them their reddish appearance. This was complex chemistry This was not simple ices. This was transformation. This was chemical evolution happening in real time on the surface of a distant world. Happening in the cold. Happening in isolation. Happening because of ultraviolet radiation from the distant sun. The questions accumulated with each new image, with each new measurement, with each new piece of data returned from new horizons across the vast distance of space. The signal traveled for hours to reach Earth. The data accumulated in computers. The images were studied carefully. The measurements were analyzed, and with each analysis, more questions emerged. The mission had revealed more than it had answered. It had opened doors that showed entire rooms full of mysteries waiting to be solved. Why was Pluto so geologically active when models said it should be dead? How was the internal heat being generated? This was the fundamental question, the core mystery. How was a small, distant, cold world maintaining geological activity? Tidal heating from Charon could explain some of it. The gravitational interaction between Pluto and Charon created friction in the interior. The friction generated heat. Energy was converted to warmth. But could tidal heating alone explain the level of activity visible in the images? Could it account for the convecting nitrogen plains? Could it account for the cryovolcanic features? Could it account for everything that appeared to be happening? The mathematics suggested no. The calculations showed that tidal heating could contribute heat, but perhaps not enough to fully explain the activity. Or was there another heat source? Was there radioactive decay inside? Most small bodies lost their radioactive heat within 1 billion years or so. After 1 billion years, most of the radioactive isotopes would have decayed to stable elements. The heat production would have stopped. They should be cold. But Pluto's orbit put it far enough from the Sun that it might have retained enough heat to remain active even after billions of years. The insulation from the cold of space might be sufficient. The heat dissipation might be slow enough. The mathematics was uncertain. The models were incomplete. The data was not sufficient to answer the question definitively. Uncertainty remained. How old were the smooth regions? How long ago had they been created? This mattered because it determined whether the activity was recent or ancient. If the smooth regions were fresh, geologically speaking, only millions of years old, then Pluto was still active. It was still undergoing change. It was still dynamic. It was active right now. If they were ancient, if they had been created billions of years ago and then frozen in place since, then Pluto had been active in its past, but might be inactive now. The activity might be historical. The world might be dormant. The age determination required understanding the impact crater population, counting craters, understanding the rates at which impacts happened, comparing those rates to Pluto's regions to estimate how long each region had been exposed to impacts. But the crater production rate in the outer solar system was poorly understood. The rate at which small bodies hit the surface was uncertain. The number of impactors out there was uncertain. Estimates varied. The calculations were approximate at best. The age estimates had large uncertainties. Could the smooth regions be young or old? Both were possible. Both fit the data in different ways. What about the atmosphere? How long could it persist? The calculations suggested decades or centuries before significant amounts froze out. A remarkably short time on geological timescales. But those calculations depended on understanding how volatile nitrogen behaved at these temperatures and pressure. The understanding was limited. Theoretical models existed, but Pluto was providing the first real test of those models. The observations suggested that Pluto's atmosphere would exist at least for a while longer, but for how long was unclear. Could it persist for centuries? For millennia? for longer? And if it did persist, how would it change? Would it grow? Would it shrink? Would it cycle in rhythm with Pluto's elliptical orbit? As Pluto moved closer to the Sun in its orbit, would the atmosphere thicken? As it moved farther away, would it freeze? The fundamental questions about how Pluto worked remained unanswered. The basic physics was straightforward. Gravity pulled inward, heat conducted outward. The orbit was determined by Newton's laws. The composition was determined by the phase diagrams of different materials at different pressures and temperatures. But the integration of all these factors into a coherent understanding of Pluto as a world, as a system, as an object with a past and a present and presumably a future remained incomplete. Understanding was partial. Knowledge was fragmented. The picture was incomplete. The questions would drive research for years, decades probably. The data from New Horizons would be analyzed and reanalyzed, again and again. Models would be refined, better models, more accurate models. Hypotheses would be tested against the observations. Some would be confirmed, some would be rejected, some would be partially right. New questions would arise from the answers. This was how science worked. This was how understanding accumulated, slowly, uncertainly, incompletely at any given moment, but always moving forward, always progressing, always getting closer to truth, even if complete truth remained beyond reach. Pluto had revealed some of its secrets: the Sputnik Planitia, the mountains, the atmosphere, the colors, but it had kept most of them hidden. The world at the edge of the solar system remained largely mysterious, deeply mysterious, profoundly unknown despite the close encounter. It would remain mysterious for years to come, perhaps for generations, perhaps forever. There would always be more to learn, always deeper layers of mystery. But now at least, we were asking the questions with real data, real measurements, real observations. We were not speculating in the dark. We were not building theories on nothing but imagination and guesswork. We were looking at a real world and trying to understand what it actually was. That was progress. That was the beginning of knowledge about the most distant place humanity had ever visited. That was the start of understanding Pluto. The journey had begun.